Thank you very much. Okay, I just changed slightly the title of my talk. We started writing of 3D nanosuperconductors using focused ion beams. And well, I would like just starting thank the organizers for giving me the opportunity to show my work here. It's a pity not to be in Turkey, and I'm trying to do my best from the screen. Secondly, I just would like just to introduce myself. So I'm a researcher in the Institute of Molecular Science at the University of Valencia, Spain. And my main research interest is the fabrication of advanced nanosuperconductors in the three dimensions using focused ion beam induced processing, mainly for applications in nanosuperconductivity and quantum computing applications. Although I'm running other different projects related to the nanoparticling of two-dimensional materials and van der Waals heterostructures, and the fabrication and characterization of hybrid, molecular, and inorganic two-dimensional heterostructures. Now here I just list some of the instrumentation, facilities, and main research methods that I'm using for the development of my projects, and most of them are located in my home center in Valencia. So what is the interest of nanosuperconductors? So novel physical phenomena emerge when the size of a superconductor is reduced to the nanoscale, particularly in the range of its current superconducting length. So such nanosuperconductors are being investigated for applications in nanoelectronics and quantum computing. And what is the interest of three-dimensional nanosuperconductors? So the fabrication of 3D nanosuperconductors could open a new world in which the geometry, topology, and chirality can be interlinking, emerging new and unconventional physical phenomena. And additionally, these materials could be very potential and very promising for the future development of multidimensional technologies. So here I show you just one example of a 3D superconducting nano-object integrating in a superconducting quantum interference device. So the three-dimensional geometry allows authors to obtain extreme in-plane and out-of-plane magnetic field sensitivity. So these devices could be used as a local approach for nanosuperconductors and nanomagnets. So how can I create superconducting nanostructures in plane and out of plane three-dimensional? So here I just mentioned that this technique is called focused ion beam induced deposition. This is just a general sketch for the in-plane application. In this specific case, we use tungsten hexacarbonyl as a precursor molecule, and this molecule is delivered from this gas injection nozzle. These molecules are absorbed from the surface, and the focused ion beam is partially decomposing, creating a deposit in the plane. And some work. Hello? Okay. Can you hear me?
Yes, we can hear you.
Okay. So it was frozen for some seconds. Okay. So just let me to mention that the Saki and co-workers reported in 2004 that these tungsten carbon nanowires drawn by using gallium focused ion beam behave as a superconductors below 5 Kelvin, and the applied magnetic field was around 9.5 Tesla. So the magnetic field can penetrate into these material creating vortices. And just to mention two works already done by our group in the last decade by using different characterization techniques, the scanning channel microscopy and spectroscopy, and those results that we obtain, we can just say that this material properly follows the microscopic BCS theory. And we have the possibility to go very narrow nanowires with gallium beam with just 50 nanometers in lateral size, and we observe a very interesting phenomenon, the entrance of the superconductivity at really a relatively high magnetic field around 2 Tesla due to the strong confinement of a single vortex at the center of this very narrow nanowire. No, it's not going. Okay, it seems very slow. So the method to draw three-dimensional nanostructure is the same, but the beam strategy is quite different. In this case, I show just one sketch of the vertical nanowire, that's a nanopillar, but if we modify the scanning parameters, we can create such a kind of complex structures like nanohelices. And I would like just to remark that the opposite beam-induced deposition is one of the most potential techniques for the fabrication of 3D nano-objects. Mainly due to its flexibility in the shape of the structures that we can create and the extremely high resolution that we can get. So this is one example of the 3D superconducting nanostructures from using gallium focused beam, the same material that we were using for in-plane structures, tungsten carbon, and the superconducting property, the critical temperature, and the electrical magnetic field is very similar to those obtained in planar structures. But if you can see here in this image, the resolution that we can get is very poor. If the diameter of these wires is just 250 nanometers, and even if there is a very huge proximity effect that avoid that we can create individual superconductors very close to each other without any kind of electrical connection. So today I'm going to present two examples of the fabrication and characterization of three-dimensional nanosuperconductors. And this is the first one, is tungsten carbon hollow nanowires using helium focused ion beam. And I use the helium beam instead of the gallium beam because its diameter is smaller, just 0.3 nanometers compared to 5 nanometers for the gallium focused ion beam. So in principle, we can obtain very narrow three-dimensional nanosuperconductors using the helium beam and also its lower proximity effect. So in this specific case, how can I create these hollow vertical nanowires? So the beam stays at the same position for the deposition time, producing two effects. The first one is the decomposition of the precursor molecules absorbed in the substrate and in the growing material, and at the same time, the beam is creating a cavity, a hole at the center of the wire, mainly due to by the helium focused ion beam milling. So just by using this very simple strategy, I was able to draw hollow nanowires with diameters down to 32 nanometers in the outer diameter and 6 nanometers in inner diameter. And the aspect ratio of these structures was around 200. You can see here the length is around 7 microns, and this is something that is almost very difficult to obtain using over nanolithography techniques. So if we modify the ion beam current during the growing from 1 picoampere to 7 picoamperes, we can tune the dimensions of these 3D hollow nanowires. And as you can see here in this plot, this is the diameter as a function of the ion beam current. We can obtain very small inner diameters from 5 nanometers to 25, and we say inner diameters, and from the outer diameters, 32 nanometers, from 32 nanometers to 140. So just by modifying the ion beam current in the grooves, we can tune the dimensions of these hollow nanowires. And interestingly, as you can see here in these movies, we can observe how the cavity, the hole, is starting from the top part of the wire and finishing at the bottom part. So at the end, we are creating hollow nanowires as nanotubes and even as nanopipettes. Regarding the microstructure and the composition of these tungsten carbon nanowires, we have to mention that the grain size is around 20 nanometers, and the crystallographic structure of these grains perfectly fits with tungsten carbon FCC structure, and the composition is very good. I mean, we obtained 72% of tungsten, and here you can see, as a comparison, the results that we already obtained in tungsten carbon wires from using gallium focused ion beam, which the grain size is very smaller, and the difference in the tungsten content that is smaller than in the case of using the helium beam. Regarding the superconducting properties, we study superconductive properties of different nanowires with different diameters, and we obtained the critical temperature was around 6.4 Kelvin, and this value is higher than the critical temperature obtained in tungsten carbon wires from using gallium focused ion beam. And also the upper critical magnetic field obtained in those nanowires was also higher than these values obtained in tungsten carbon grown by gallium focused ion beam. So just by using the helium focused ion beam, we can obtain three-dimensional hollow nanowires with better resolution, higher aspect ratio, higher crystallinity, higher purity, and improved superconducting properties. Let's move to the second example on the 3D nanosuperconductors, and it's the fabrication of tungsten carbon nanohelices using the helium beam. And in this case, we just modifying the beam scanning to create such a kind of nanohelices. And you can see here some examples. The diameter of the nanohelix was around 100 nanometers. And just modifying the partner diameter, we can tune the nanohelix diameter, and modifying the dwell time, which is the time at which the beam stays in each position. We can modify the length term of each nanospiral, as you can see here. So just modifying dwell time, we can tune the length of the term from 200 nanometers to at least 900 nanometers. So here I show few examples. I was trying to maintain the diameter of this nanohelices around 100 nanometers and modifying the length of charge from 200 nanometers to 1 micron. And you can see how these nanohelices look like and the length of each one that they were in the microscale. On the other side, I was trying to keep the diameter of the nanohelix around 250 to 300 nanometers and the length of the charge from 430 to 2.3 microns. So I would like just to remark that just modifying the diameter of the nanohelix and the dwell time, I was able to draw really completely different three-dimensional geometry nanohelix. Regarding the superconducting properties of these nanohelices, I just studied few of them for comparison. These two type 1 and type 4 almost the same diameter, around 100 nanometers, and the difference was the length of the tar from 200 to 550. And type 6 and type 7, just to observe that the properties were similar for nanohelices with 300 nanometers in diameter and modifying the tar length from 430 nanometers to 900 nanometers. And interestingly, we observed that the main superconducting properties, the critical superconducting temperature and the upper critical magnetic field, was very similar for all of them. And it was very similar also to the values obtained for hollow nanowires already studied. So this is giving us an idea about how robust are the superconducting properties of these nanohelices with completely different three-dimensional geometry. And an interesting feature was observed in one of these nanohelices, the type number 6, in which we observed the superconducting transition is going through the superconducting state to this normal state in different steps, as you can see here. And these steps are related to the occurrence of phase slips. It was our interpretation based on numerical simulations, based on time-dependent Landau equation. You can see in this plot how the superconducting of the parameter at these 4 different regions, and at the number 4, we are observing the vortex patterns on this structure, and how when we are increasing the current, 2 phase slips regions emerge, inducing this jump in the resistance. And in the region number 2, 2 more phase slips regions are emerging, producing the next step in the resistance. And I would like to remark that this phenomenon was not observed in planar structures, and is giving us an idea how we can tune and modify the superconducting properties on three-dimensional superconductors. And I just would like to summarize the main results of my talk. That's the fabrication and characterization of individual superconducting crystalline tungsten carbon hollow nanowires with better resolution and improved superconducting properties, and also the fabrication of individual superconducting nanohelices with real dimensions, and that we at least prove that given its helical three-dimensional geometry, we observe experimentally fingerprints of vortex and phase slip patterns, which are supported by numerical simulations based on time-dependent Landau equation. I would like to finish this and thank my collaborators in this work, Alfonso Ibarra and Jose Maria de Teresa from Zaragoza, Spain, Dominique Meilly from Palazzo, France, Roman Rezaed, Ekaterina Smirnova, Oliver Smith, and Vladimir Fomin from Dresden, Germany, Ulrich Sechter from Nijmegen, the Netherlands, and Isabel Guillamon and Herman Söderer from Madrid, Spain. Also, the helpful support of the technical staff in the lab, Laura Casado, Isabel Rivas, and Ruben Valero. And of course, the financial support of different agencies. And of course, thank you very much for your attention.
Thank you very much, Rosa. Nice results, great presentation. I'm just wondering what materials are currently available for this three-dimensional type of growth. So,
do you mean from superconducting?
Yeah, superconducting materials. Yeah.
From my knowledge, there is just this one and another one based on niobium and carbon.
Uh-huh.
I think it's the precursor is not commercial available, and I think this was synthesized by a group in Frankfurt, but I'm not pretty sure about that.
So what you're doing is based on mostly on tungsten, right? So like the only material available, right?
Exactly.
Yeah. Thank you very much.
You're welcome.
Are there other questions? Are there any through Zoom? Okay, so I have a couple questions. A couple practical questions. I was curious how you move your nanowires and helices over to then make a transport device. So it's you're fabricating it vertically, and then how do you move it over?
Yes, in this very cheaply because it's clear that they were done in a vertical way, and just to put in plane to do the electrical characterization, I was using a nanomanipulator that is mainly used, for example, for the liftoff of TM lamella preparation. So, well, I was just to push there and try to put in plane using this nanomanipulator. And later on, I was making the supporting electrical contacts, also using the platinum based on focusing induced deposition.
Okay, great, thanks. And then also another kind of practical question. How long does it take to fabricate one of these?
Maybe just 2 minutes more than this.
Okay, wow, it's pretty fast. So then do you know the penetration depth of any of your nanowires or your helices?
And the penetration that we mean from the superconducting properties?
Yes.
Yes, yeah. I mean, the current method, it was around 4.55 nanometers, and the penetration there around 450 nanometers.
Okay, so then I was wondering, when you apply a transport current, then wouldn't you get like a kind of a self-field effect from the current that would end up effectively narrowing like the superconducting region? And then I was also curious if that was accounted for in these simulations.
Yes. In principle, this current length and penetration therefore included in the simulation. Of course, any experimental data that we provide to the simulations we're implementing on them.